Hello, everyone. I'm Dennis Burrell from Ventive, and what are you doing up here?
I'm supposed to walk on external antennas with AFC and standard power.
No. I was supposed to do my presentation on Harry Potter and the wizardry of Wi-Fi antennas.
So what are we supposed to do then?
So I can't do that?
I guess we'll have to do something together.
What? Keith, what happened? So I can't do any of my Wi-Fi spells?
I guess not.
Like ether connect them?
You know, I do have an idea of something that we can do together, though.
Okay, what
something that we both love.
Okay.
How about some common antenna misconceptions?
All right.
Yeah.
So last year, both of us presented up here at WLPC, and someone threw out something from the audience saying, how about you two antenna guys get together and do a presentation? So we talked about it, and we decided that we would do it. And unbeknownst to us, when we started this, we were friendly competitors, but that's no longer the case. So.
But still, it'll be good to come up here, still show that unity with each other, so I'm always glad to be up here with you, Dennis.
Exactly.
So as we kind of get into this, we're going to go over what is a misconception, and when we're covering this, we're kind of both considering this as what is something we often hear from our clients when we're on calls. So it's something that they say, we're like, that's not really how that works. And then we have to go through the process of explaining how it actually works on the antenna side. For some of these, y'all may know that this is the case. But you may not know the actual reasoning behind it. So even if you maybe know that it's not a truth, getting that detail behind it is going to be very beneficial, I believe.
Right.
So the first one that we have up here is that a higher gain antenna is always going to be better in my environment. Typically in this group, I don't hear that too often, but it does come every now and again where, I have this big warehouse. I just need to slap a high gain antenna in there. Doesn't matter what it is. I'm good to go. But that's not the case. It really depends on your specific deployment, what the requirements are, what the coverage area is. And we can see this when we actually go into those individual coverage areas especially. So if you're trying to cover a really wide area versus a very narrow area, having a higher gain antenna isn't going to help you as much. You may need a lower gain antenna that has much wider beam width. So determining that versus just going high all the time is very vital. Same thing can happen in a warehouse environment. You may have a really good antenna. The one on top there, for instance, is similar to the 9104. It doesn't have all the bells and whistles, but high gain, 20 by 20 degree. But if you drop that down to a 15, 20-foot height, those side lobes on that are very large in relation to the main lobe. So you're going to see that bleed over and bleed out everywhere versus using a lower gain antenna. You're not going to notice that much, and that's probably a better choice.
So let's see. So what about this one? The bigger antenna equals a stronger signal.
Hear it a lot.
Yeah, we hear that all the time. So if the antenna is physically larger, it must be a higher gain and provide a better signal at my client device. That's not the case. In fact, there are many contributing factors to the size of an antenna: gain, beam width, efficiency, polarization, the number of elements in the antenna, and also how it's tuned for frequencies, the frequency bands that it operates in, and many others. So what we have here is our two antennas. The one on the left is a Ventive small form factor antenna that's actually 6 dBi in gain across the band. And then if you look at the size, it's 3.4 by 3.4 inches. It's a 4-port antenna. Now we have a 10-port antenna that's only 4 to 5 dBi across the band. But because it has more ports, it has to be larger. And if you look at the size, it's 11.8 by 11.8. So it just depends on the application. Bigger is not always better. You need to look at specifically what your application is, what type of efficiency you need, what kind of gain, beam width, visual, all of those types of things.
Misconception number 3 I always hear is, these external antennas have so many fantastic properties. I need to put this in everywhere I go. While we would love that is beneficial for us, most scenarios are in an office or carpeted office space or in a hospital. Some education areas can use directionals, but a lot of times using the internal antennas that the manufacturers provide is a perfectly good solution. We are going to leave it there. We are antenna guys still, so we're not going to give you too much more insight on that.
Yeah, but let's ask them a question. How many of you design with external antennas? What about internals? So we know that in the market, there's probably 90% of the APs sold are internal antennas, right? There's always that niche application, warehousing, large public venues, those types of things like Jim Flork was talking about today with large public venues and their antennas. There are always certain applications where you're going to need an external antenna. So while we would like to sell a bunch of them, we know that a lot of you in here do a lot of designs with internal antennas. So antennas operate uniformly across all tuned frequencies. So if I got a tri-band antenna and it's designed to operate at 2.4, 5, and 6 gig, it's going to be uniform across that. Specifically, if I say I designed the 6 dBi antenna. That's not always the case. In fact, in the real world, that's what you would assume that it is, but the antennas will vary across the frequency band that it's tuned for. So right here, what we have is we have the VISWAR, voltage standard wave ratio of an antenna that's tuned at a tri-band, 2.4, 5, and 6 gig. And as you can see down at the bottom, which is the lower VISWAR is what the antenna transmits versus what's reflected back into the radio once that is connected to it. Great VISWAR is typically 2-to-1. That's where approximately 90 to 92% of the power is transmitted out, as opposed to the other remaining 8 to 10% going back into the radio. But as you can see, it's not uniform. You see a lot of ripples down there. And if you look at the gain and the efficiency, that's where that ripple represents the change in the gain and the efficiency numbers across the frequency band of operation.
So the other main thing that we hear is, oh, well, I have a fantastic antenna. It's going to cover a wider area. That's good. That's all I'm using it for. But it does more than just that. It's not only covering a wider area sometimes, depending on which one you're using. It also can improve the actual performance of your network. Why does this happen? So when we actually look at our MCS tables, we can see that one of the main considerations when you're determining this is your modulation rate, or MTS is your modulation. And a primary factor of that is your RSSI and the SNR values in your environment. So if you have an antenna that's causing it to either have smaller, tighter cells where they're not noticing the outside interference, or there's a higher gain innately, so you're getting a better signal coverage at that individual spot, you're going to see a better SNR, going to probably get better MCS rates overall. And this is mainly due to the QAM that we see here, the quadra amplitude modulation. So when you get into that 4K and you're getting all those individual changes that are very minute, having that clean signal is very important to be able to actually interpret those minute changes.
So let's talk a little bit about directionals. Directional antennas only cover a small spotlight area. A directional antenna will act as a spotlight, only providing coverage in a small cell-based area. So the way that we look at directional antennas is you think of your flashlight, your high beam flashlight. When you turn it on, it shoots in a specific direction, as opposed to, say, when you come into a room and you turn on a light. You get light everywhere, simulating somewhat of an omnidirectional, right? But with the directional, the more that you concentrate that beam, the less that beam width, the more the coverage area. But the fact is, there are many types of directional antennas. You have some high gain, you have some medium gain, you have some low gain directional antennas. And that's based on the beam width. You can have symmetrical or asymmetrical beam widths. The antenna on the left is a high gain antenna, shows a narrow beam width, as opposed to, say, the antenna on the right, like a 6 dBi or something antenna, or a warehouse antenna that has a large horizontal beam width, right? It covers a lot, but the difference between the two is on the gain and on the beam widths, right?
Client AP transit power mismatch is another one that we commonly hear. Hopefully y'all watched a presentation I did in Prague. This goes a lot more in depth on this, or my podcast with Keith. We went into a lot of depth, but people often think, oh, well, if I'm still super far away, my client device is never going to be able to talk back to the AP. No matter what happens, it's just a matter of physics. But that's not necessarily true. Given that an increase in antenna gain is a bidirectional increase, your client device will actually be able to hear that AP from farther away, and vice versa, the AP will be able to hear the client device. So this does improve the overall distance that you typically be able to cover with the client device. And you can always imagine this kind of as the old megaphone example. Not only are you speaking louder through the megaphone by cupping your hands, but you're also hearing louder by putting it to your ear. It's the same concept.
So let's see. All antennas are created equal. It doesn't really matter what antenna I put on my device. They're all basically the same if they have the same gain and beam widths. The fact is, many inexpensive antennas on the market may advertise certain specifications, but their actual performance can differ significantly once deployed. So this could be because they are low quality, the VisWAR is bad, like I mentioned earlier about VisWAR. A good VisWAR is 2-to-1. They could be higher VisWAR across the band, and the materials that are used are inferior. So here's your inferior antenna that someone may have got on Temu because they thought they was getting a great deal on the antenna, purchased the antenna, hooked it up, thought they were going to get great performance, but contrary to popular belief, it didn't happen. So, and these are just some of our antennas. So with antennas, one of the main things that we look into is quality, right? Quality across the band, consistency across the band. You want to look at the cables that you're using, especially at 5 or 6 gigahertz. Typically, we use a low loss cable, right? Because at the higher frequency bands, you're going to get more loss per square foot across the cable. So those are all the types of things you have to take into account, as well as the manufacturing. Put in standard good manufacturing processes so that your antennas are repeatable once they're being manufactured. And then we also test 100% once they come off the line to make sure that they're meeting the specifications that's set for the antennas.
David Coleman and I believe one other already had a good conversation today, or this week about location services and using 802.11az. But a common one that we hear is that, oh, well, if I increase my antenna or change my antenna from what the manufacturer is recommending, that's going to change up all my location services. It's not going to work right. Luckily, we have not used RSSI values to do location services for a long time now. It's mostly dependent on a fine time measurement and time of flight. And this is all dependent on basically just using the speed of light. So it's really independent of whatever frequency you're using or whatever gain you're using. It's all that goes back to that constant to actually determine that ranging that you're using. So independent of that, you can swap your antennas and all your locations will still be accurate.
Antennas provide more range at lower frequencies. If you can see to the picture to the left, you see a frequency, a high frequency, and a low frequency sinusoidal pattern of the frequency band. So a multi-band antenna will have more range at its lower frequency compared to its higher frequencies. In some instances, that is true, but it's not specific because of the frequency band, right? So low frequency waves will generally propagate through materials more easily than high frequency waves. Some of you guys will see that when you're doing your predictive designs on your Ekahalo or your Hamina, right? Or Hamina. You'll see that your coverage at 2.4 is much larger than your coverage at 5 and 6. And then if you're going through any types of interferes or any types of attenuation set, the coverage is even smaller once it goes through those attenuations. That's not specifically because of the frequency of the antenna, but it's because of the amount of power that's received in the antenna, which is directly proportional to the effective aperture of the antenna. So what we have here is the equation to calculate the effective aperture of an antenna. And as you can see, at the frequencies 2.4, 5, and 6 gigahertz using a standard 6 dBi antenna, you can see the difference in effective aperture. So you're going to get, with the larger aperture, you're going to get more of a transmission, more power, as opposed to 5 and 6 gigahertz. Now, one of the things, if you're looking at this, so how do I make this better? So what you'll see in some of our antenna designs is that you'll see the gain of the antenna at 2.4 is lower than 5 and 6 gigahertz, right? Because the reason why is that the higher gain, I'll be able to have a larger effective aperture compared to the 2.4, so I'll get more coverage, more transmission. So if you're doing your heat map, you'll see a larger heat map for those specific frequencies. Now, another thing with this is, so going through these calculations, in order to get the same effective aperture at 2.4 that I have at 5 and 6 gig, for instance, at 5 gig, I need approximately a gain of almost 12.5 dB on the antenna. And then at 6 gig, I need about 14 dB on the antenna. Now, if I come out and I'm trying to sell you an antenna for indoors, a directional antenna, and it's at those gains to have the same or equal coverage so that when you're going through attenuation and interference and those types of things, and we're talking about aesthetics, you're not going to purchase that type of antenna because it's going to be extremely large based on that frequency, based on those gains at those frequencies. So what we try to do is we try to balance aesthetics, the size of the antenna, the performance of the antenna. So all of these things we take into account when we're designing our antennas to give the best product for whatever you need that performance for. And one thing about antennas, an antenna works as well as you want it to work depending on what your application is and what you're trying to do with the antenna. So you may have to sacrifice front to back ratio or some of those types of things in order to have an aesthetically pleasing design. But the one thing that we'll always say is take the data that we have, the majority of our antennas are in Ekahau and Hamina. Just go in and do the predictive and everything and then test and see how it comes out.
Now, we have a little bit of an internal debate going on, or newly internal debate, that I think we're going to need y'all's input on. So, we need y'all's decision on which way to go. Do we go Exceltez or Ventex? So feel free to add us on social media with your choice of those two. We'll be waiting to see which one wins out.